In this lesson, we're going to take a look at atomic mass in the periodic table and how those values are determined. And they're based on taking averages of the different isotopes. So if we go back to our previous lesson on isotopes, recall that isotopes are elements that have the same number of protons, so they're the same element, but they have a different number of protons. So if I look at the two different atoms here, both of them have 6 protons in their nucleus, and so both of those are going to be carbon atoms. This carbon atom has 6 neutrons in it, whereas this has 7. Because protons and neutrons have a mass relative to one another that is the same, and we use 1 to show the mass of each of those, the total mass of this carbon atom is going to be 12 in what we call atomic mass units. And for this carbon atom, we have 6 and 7, so a total of 13 atomic mass units. So the mass of each of those is different. So when we look at the mass that is given to us in the periodic table, it's based on the fact that more than one isotope exists for a particular element. The number, though, is often, so we're going to take a look here at 3 different elements, and the top number that's listed here is the atomic number, or the number of protons. And then the number down here is the atomic mass, which is the number of protons and the number of neutrons, so the total. So as you look at those numbers, what you notice is very different about the numbers we see up here versus the numbers we see for the mass number, the atomic mass. So in the periodic table, every single atomic number that you will see is a whole number. So remember, that represents the number of protons. So 15 protons means we have the element phosphorus, 16 means we have sulfur, 17 means we have chlorine. The atomic mass, on the other hand, as we look at that, that is not a whole number, yet it represents the total number of protons and neutrons, and we're not getting a whole number. And that is because of different isotopes that exist of each element. And so the number that we get for the atomic mass is based on an average that we calculate. And if I look at chlorine, chlorine has isotopes 35 and 37. And if I were to just calculate an average of 35 and 37, I have 2 different things I'm calculating there, so I'm going to divide by 2. The average there would be 36. Yet the average in the periodic table, so the atomic mass there, is not 36. And that's because I don't have equal amounts of each of those isotopes. So if I had equal amounts, then I can add them together, divide by 2, and what that does is it gives an equal weighting to each of those. So if I have 2 things I'm splitting by, each of these has a weight of 50%. So half of my sample would be 35 and half would be 37. And in that case, my average atomic mass there would be 36 atomic mass units. But once again, as you can see, that's not the case, which means that we're not going to have an equal weighting. So determining the atomic mass based on the average mass that each different isotope represents of the mass means we're going to need to do a weighted average. And we'll take a look at what that looks like. So the atomic mass listed in the periodic table is based on a weighted average. So not equal amounts given to each of the isotopes, but based on the percent of it found in nature. So for example, the element hydrogen can have the isotopes protium, deuterium, and tritium. the atomic mass listed in the periodic table is 1.0079 atomic mass units. And that is based by taking the percent of protium that exists and the percent of deuterium and the percent of tritium. And that will give us the average atomic mass, or the relative atomic mass. So that's based on the relative amounts of each of those three isotopes. Now, looking at the fact that this is very close to 1, that tells us that hydrogen 1, or protium, is going to be the largest percentage of hydrogen that is made up. So once again, percentage of each of the different isotopes all added together will give us the average mass, or the atomic mass, which we find in the periodic table. When we take a percentage of something, our percent gets converted to a decimal, and of means a multiplication. So this would be converted to a decimal and multiplied by the mass for hydrogen 1, or protium, and then the percentage converted to a decimal multiplied by the mass of hydrogen 2, or deuterium, and so on. So the general formula there, depending on the number of isotopes that exist, percent of the mass of each one, and then all of those added together will give us the atomic mass. And the way that we find out the percents of each of those is through an instrument called a mass spectrometer. So once a sample is put into a mass spectrometer, it can tell us what percent of each of the different isotopes exist in a particular sample. Okay, so we're going to look at two different examples, so two different things that we can calculate. So in our first example, we have silver, which has two stable isotopes. One of them has an atomic mass of 106.904 atomic mass units, and the other one is 108.905 atomic mass units. The first one represents 51.82% of the mass of the element, and the second one represents 48.18%. So what is the atomic mass of the element silver? So atomic mass is equal to percent of the first mass and added to percent of the second mass. So I have 51.82% of 106.904 and 48.18% of 108.905. So this is how we calculate the weighted average. So I am making the worth of this mass slightly more than the worth of this mass because there's slightly less of the overall sample made up of this mass. So this is how we do weighted averages. So converting a percent to a decimal, so dividing by 100, means that I'm going to move my decimal place over 2 to the left. So 0.5182 of means times 106.904 and 0.4818 of 108.905. And I can plug that all into the calculator in one go, and that is going to give me 107.868 atomic mass units. So the atomic mass for silver is 107.868 atomic mass units. And I can double check that in the periodic table. And so I can see here that 107.868, and this one is more precise. So we have more decimal places there, but we had 868, so that is correct. Okay, the other type of question that you could be asked to do, and this is going to bring back some skills from grade 10 math of substitution. So chlorine has two isotopes. We just talked about this earlier, chlorine 35 and chlorine 37. So chlorine 35 has a mass of 34.96885 atomic mass units, and chlorine 37 has a mass of 36.96490 atomic mass units. The average atomic mass, and this is in the periodic table, is 35.453 atomic mass units. So we're going to calculate the isotopic abundance of each isotope. So isotopic abundance means how much, and then for each isotope. So what percent of the sample is chlorine 35 and what percent of the sample is chlorine 37 is what we are looking for here. Now you can see here chlorine 35, this rounds to 35, and chlorine 37, this mass rounds to 37. The masses for most things are slightly off, so the way that they have calculated what the mass of one proton or one neutron is by taking carbon 12 and dividing by exactly 12. And so that's how they found that out. And so as we look at different elements, once they take the mass of those, the numbers are usually slightly off. But you can see here we're talking about hundredths of an atomic mass unit, because up until here that would round to 35. So this is the first place that is different there. So the atomic mass we know, so 35.453 is equal to some percent, so I don't know, I'm going to use an X to represent that, some percent of 34.96885 and some other unknown percent, different amount, of 36.96490. So these are my two different samples, the two masses that they have, so chlorine 35 and 37. And I have some percent of each that makes up my total sample, which would give me a relative atomic mass of 35.453 atomic mass units. So this is my total sample, both of these, which means in total this would add up to 100%. Now since these are representing decimals, because I have to convert the percents to decimals, x plus y doesn't equal 100, but 1, because I would have divided by 100. So x and y in total add up to 1. And what I'm going to do is I'm going to rearrange that equation. Doesn't matter whether I rearrange it for x or for y. So if I leave y on this side, 1 was on the other side, I'm going to move x over. So right now x is positive. I'm going to move it over by subtracting it. And now I have something that I can substitute in for y here, so that I don't have two different variables, because I can't solve if I have two unknown variables. I'm going to keep my x. That I'm going to move to the back, so coefficient comes first. Just a fancy name for the number that comes in front of my variable or the thing I don't know, and I'm using a letter to represent it. Y is the same as 1 minus x, and that gets multiplied by 36.96490. I'm going to use distributive property here, 1 times the 36.96490 and negative x times the 36.96490. So 34.96885x plus I have 1 times 96.96490, which is just 36.96490. And then I have a negative x times positive 36.96490. So that's going to give me negative 36.96490x. I'm going to now write my 35.453. So now what I want to do is put my variables together on one side and then my constants together on the other side. So I'm going to move my positive 36.96490 over, so it's an addition here. To move it, I'm going to subtract it. So I have 35.453, subtract 36.96490, and then on the other side, whoops, there we go. That's what I'm looking for. Okay. 34.96885x, subtract 36.96490x. So as I simplify these, I'm going to end up with negative 1.5119 and negative 1.99605x. Now to isolate my x, to solve for x, I'm going to undo the multiplication between negative 1.99605 and x by dividing. And that's going to leave me with 0.757. If I remember correctly, there were 4's after that, so I'm going to stop there, and that leaves me with x. So x is equal to 0.757. As I convert that back to a decimal, I'm going to move my decimal places in the opposite direction, or multiply by 100. So 75.7% is what x is equal to, and that was for chlorine 35. So 75.7% of the sample is chlorine 35. And then to solve for chlorine 37, y is equal to 1 subtract x, which is equal to 243, or 24.3%. So chlorine 35 is 75.7% of the sample, and chlorine 37 makes up 24.3% of the sample. So we have much more of chlorine 35, and so it makes sense that the atomic mass that's listed is actually a number that is closer to 35 than it is to 37, or even halfway in between at 36. All right, there's 2 practice questions here, and the answers, I'll just, pop up here. So you can try these questions on your own, check to see if you have the correct answers. So they're the same type of question as example 1 and 2 that were just done, and then we'll look at some more practice problems in class tomorrow.